So the next section in your textbook takes a look at different types of chemical reactions. And so a chemical reaction is how chemical bonds are formed, which is what we were just talking about in the last recording, chemical bonds. And so chemical reactions are when new chemical bonds are formed between atoms or when existing bonds are broken. So it could be either way. The bonds are either formed or the bonds are broken. And there's three key chemical reactions in physiology that we'll be talking about. But first, some basic energy concepts. Reactants are rearranged to form products. So reactants are the molecules or atoms that undergo the chemical reaction, and then products are the substances that the reactants are arranged to form. That's what comes out of the chemical reaction. And then the sum of all the chemical reactions in the body is called metabolism. So some basic vocabulary for you there. Now I used the word energy already, and energy is the capacity to do work. So if you have to define it, energy is the capacity to do work, and energy comes in two different forms: kinetic and potential energy. Now, kinetic energy is the energy of motion, and potential energy is stored energy. So keep in mind that energy can be converted from one form to another, and oftentimes heat is a byproduct of this conversion. And I mentioned in the other slide that there are three types of chemical reactions important to this general anatomy and physiology course, and we'll start with decomposition. So decomposition is when it's a chemical reaction that breaks a molecule into smaller parts. Okay? And in the body, these are often hydrolysis reactions. Hydrolysis reactions. And if you take that word hydrolysis and you break it into two parts, hydro meaning water and lysis means to break. So in hydrolysis reactions, you're taking a molecule of water, that H2O, and you're breaking it apart. Okay? And when you break apart a molecule of water, you get a hydrogen ion and a hydroxyl ion. And you take those two little parts and you stick them to either end of this now broken AB compound. Okay? And so you get this sort of an outcome. Okay, so that's a hydrolysis reaction, decomposition. And so when you have decomposition reactions, typically hydrolysis reactions happening in the body that release kinetic energy for work, that's called catabolism. Okay, so catabolism is decomposition, is breaking things down, is breaking apart of water. I think of a catastrophe is a catabolism, where things are blown apart or broken down. Catabolism and catastrophe, help me remember those two, that decomposition happens in catabolism. Just a little trick for you. I don't know if it'll be helpful or not, but that's one of the ways I remember it. And so the second type of chemical reaction I bet you could figure out is then a synthesis reaction. So in synthesis reactions, you're making larger molecules from small parts. So you take little parts, like in this example you have A and B, and you combine them to make a bigger molecule, so AB. So we are synthesizing larger molecules. And this is often called dehydration synthesis because, again, water is involved. So we're going to dehydrate our A compound and our B compound. And when we dehydrate them, that means we pull hydrogen off of one and a hydroxyl off the other. And when you combine those two, you make water. So we're dehydrating our two reactants, and you're producing water as a byproduct then. So we call them dehydration synthesis reactions. And so this form of metabolism is called anabolism. Anabolism is when you're building bigger molecules, and it's typically we're building storage molecules in the body. And the last type of chemical reaction that is important in general A&P is exchange reactions. And really, this is just a combination of decomposition reactions followed by synthesis, and so the outcome is an exchange. So this is where you have a shuffling of parts of the molecules, so it's like they're trading dance partners, if you will, a do-si-do. And so that's considered an exchange reaction, and those are your three key reactions. But most of our important biological reactions are what we call reversible reactions. And when we're writing out these reversible reactions, as you'll see later in the semester over and over again, you'll see these two opposite arrows. So instead of just an arrow from left to right, as I've been showing in the previous slides, you'll see an arrow that has a pointer going either left or right, meaning that at chemical equilibrium, the rates of the two reactions are in balance. It's being broken down as fast as it's being built. So this is a completely reversible reaction, and it doesn't slide to either side in an equilibrium type of situation. And so we're at another checkpoint, and so I'd like you to pause the recording and see if you can identify and describe three types of chemical reactions that are important to human physiology. And after you feel confident with that answer or that response, then you can go ahead and continue the lecture recording. So section 2-4 in your textbook takes a look at enzymes. Now it's important to know that many of the reactions that I've just described would happen on their own. However, the amount of time that would be required for the reactants to undergo the reaction and generate the products would take a very, very long time. And so that's where enzymes come in. Enzymes aid in chemical reactions because they lower the activation energy that's required to start a reaction. And they typically can do this. They lower this activation energy by bringing reactants closer together or by putting a stress on a chemical bond that we want to break. And so by doing that, they lower the energy required to make that chemical reaction occur. And so enzymes are referred to as catalysts. They're biological catalysts because the enzyme themselves is not changed by the chemical reaction. So the enzyme can be used over and over and over and will facilitate many, many reactions before they're simply worn out. So enzymes are considered biological catalysts. And so this picture that we have here is trying to denote the amount of energy required so for a chemical reaction to occur. And so on the left here we have energy. As you go up this way, it's an increase in energy, and this is the progress of the reaction. So this is kind of like time on this axis. So here you have your reactants that have this much energy. And in order for them to generate product down here, they would have to overcome this big hump of activation energy. But if you have an enzyme, they only require this much energy in order for the reaction to proceed. And then eventually the product has less energy than the reactant. So in this type of a reaction, you would be releasing energy, possibly in the form of heat. And so what that figure is trying to depict is what we call an exergonic reaction, because the products had less energy than the reactants. And so exergonic reactions release energy. Energy exits from the reactants. So exergonic. And so, like I said, most of this energy is dissipated as heat. And this is one of the ways that your body can actually regulate its temperature by having your muscles burn energy molecules and release that heat and keep your body warm. And so on the flip side then, endergonic reactions require the input of energy. So they're said to absorb energy or take up or spend energy. So ender, that word part, means in, whereas X means out. And so this is referring to energy consumption or energy release. So if you wanted to try and assess your learning here on these concepts, you could take a look at this figure again and try and draw the figure to represent an endergonic reaction, because I told you this is an exergonic reaction where the reactants have more energy than the products. So if you wanted to draw an endergonic reaction, the product would be, do you want to pause the recording and see if you can figure it out first before I tell you the answer? Go ahead and try that. Okay, so if you wanted to redraw this figure to represent an endergonic reaction where the products have more energy than the reactants, instead of the product being down here, the product would be up here, because this is our scale of energy. So if the product was up here, this would represent an endergonic reaction where there's more energy in the product than there was in the reactant. So some more vocabulary terms for you here. The rest of the chapter focuses on nutrients and metabolites. So nutrients are essential elements and molecules that are obtained from your diet. And metabolites include all of the molecules, including nutrients, that are synthesized or broken down by chemical reactions inside of our bodies. And like all chemical substances, nutrients and metabolites can be broadly categorized as either inorganic or organic. So an inorganic compound is small, usually without carbon or hydrogen, where organic compounds are typically very large and complex, and they have to, and this is important, they have to have a carbon and hydrogen as part of their composition. The most important inorganic substances in the human body are water, carbon dioxide, oxygen gas, acids, bases, and salts. And the remaining sections in your textbooks, sections 2-9 to 2-13, are going to address these major organic substances in the human body. Now, keep in mind, when I'm talking about organic versus inorganic, I'm not talking about that section in your grocery store that sells food but doesn't have any pesticides or hormones. I'm talking about basic chemistry here, the presence and absence of carbon and hydrogen. So the next section in your textbook takes a close look at water. Water is probably the most important substance in your body. It makes up 2/3 of your total body weight. There's 3 general properties of water that are particularly important to our discussion of the human body. The first is that water is an essential reactant. It's an essential reactant in the chemical reactions of living systems, and those main chemical reactions I told you about are dehydration synthesis or hydrolysis reactions. So remember, just as a review, dehydration synthesis is where water is released, while molecules of a product. And then in hydrolysis reactions, water is absorbed. Okay, just as a little review there. So the second quality or property of water is that water has a very high heat capacity. A high heat capacity, very high specific heat, which means that it requires a lot of energy to change the temperature of water. And so and you may have experienced this if you've gone into any body of water, like a lake or a river in Wisconsin. In the spring, that lake is really cold. Even though the air temperature might be 80 degrees, the water is still really cold. And then in the fall, even though the air temperature is cold, the water temperature of that lake is still warm. That's because water has a very high heat capacity. And so this is one of the reasons, if you could call it a reason, that our body is 2/3 water. And it's very easy for us to then maintain homeostasis maintain a constant body temperature, because most of our body is made of water, and water has a very high heat capacity. And last but certainly not least, water is an excellent solvent. Most of the chemical reactions in our body occur in water because it dissolves many solutes. The ionic bonds are going to dissociate in water due to its polar bonds, and this gives it the capacity to conduct electrical currents too. We have a number of electrical conducting systems that we're going to tell you about in the upcoming chapters. And so this figure is showing water dissolving the ionic bonds that hold sodium and chloride together, and how we can then have these solutes that are dissolved in water, and how water kind of binds up or associates around each one of these molecules. And notice how water is facing these molecules differently. Remember, water has polar covalent bonds, and notice how the positive ends are those blue hydrogen portions that are positively charged are facing the negatively charged chlorine, whereas if you look at the sodium, the Na that's positively charged, you can see that the negative oxygen molecule of the water is facing that positively charged sodium. Remember, opposites attract. And so this is one of the ways that water can dissociate these ionic bonds and create solutions for us. And so we've reached another checkpoint box where I'm going to encourage you to take some time and see if you can answer these questions on your own. What is an enzyme? How would you define it? And can you distinguish between inorganic and organic compounds? And after you feel comfortable with those concepts, then you can go ahead and start the next lecture recording.